Hey everyone, welcome back. In this video, we are going to discuss some types of relations. Actually, there are several kinds of relations. I have just mentioned some of them. As you can see, there are several types of relations. Number first is reflexive relation. Number second is identity relation. And number third is transitive relation. And the fourth one is symmetric relation. In this video, we are going to discuss just one of the relations, and reflexive relation. Here is the definition of reflexive relation. If I have a set A which is non-empty set, what does it mean, or what does it take for a relation R on a non-empty set A to be reflexive? Here is the definition, and it will answer this question. A relation R on a non-empty set A. Note that my set A is non-empty. So, a relation R on a non-empty set A is reflexive if every, note down, I have highlighted this every, and it is a universal quantifier. If every element A of the set A is related to itself, that is R, which is a subset of A cross A, is reflexive if this thing happens. What? If every element of A is related to itself through the relation R. I can write down this symbol this way as well. So, a relation R on a non-empty set A is said to be reflexive if every element of the set A is related to itself through that relation R. It means that according to this definition, if you can find at least one element in the set A which is not related to itself through the relation R, then that relation is not reflexive. So, in simple words, this definition tells me that if I have a non-empty set A and I have a subset R of A cross A, I will say that this subset R of A cross A defines a reflexive relation on the set A if every element of the set A is related to itself in the relation R. Let me take some examples to explain what this definition tells us. Here is my first example, and in this example, I have set A whose elements are 1, 2, and 3. And I have a subset of A cross A denoted by R and is defined by this. The elements of the relation R are the ordered pairs 1, 1, 2, 2, 3, 3. My job is to find whether this relation R, which is a subset of A cross A, whether it is reflexive relation or not. For that, I will simply apply the definition of being reflexive to this particular example. Now, this relation R on the set A is reflexive if every element of the set A is related to itself. So, what are the elements of the set A? Clearly, 1, 2, and 3. So, for the relation R to be reflexive, 1, 1, 2, 2, 3, 3 must belong to the relation R. And as you can see, R includes all these three ordered pairs. So, by definition, this relation R on the set A is a reflexive relation. Here is my second example. And in my second example, I have the set B whose elements are 2, 6, and 8. And I have a subset of B cross B denoted by R and whose elements are these. And my job is to find simply whether this relation R on the set B defines a reflexive relation or not. For that, I will simply apply the definition. After applying the definition, I get that this relation R is in fact a reflexive relation. Why reflexive relation? Because this relation R is a reflexive relation if every element of the set B is related to itself through the relation R. That is, all the ordered pairs whose elements are 2, 2, 6, 6, 8, 8 must belong to the relation R. And as you can see, all of these three ordered pairs are there in the relation R. So this example second also satisfies the definition of being reflexive. So by definition, R is a reflexive relation on or in the set B. I have my third example here. And in my third example, my set is simply the well-known set, the set of natural numbers, which is also known by other names such as counting numbers, positive integers. And I have a relation here defined on the set N. And the relation is M divides N. Now I am going to collect all those ordered pairs in the relation R which satisfies this condition, the condition of being factor of other, or the relation of M divides N. So as you can see, we know from high school mathematics that every natural number divides itself. If every natural number divides itself, it means that every natural number satisfies this property, the condition of being divisible by another natural number. So if every natural number divides itself, it means that 1 divides 1, 2 divides 2, 3 divides 3, and in general, N divides N. So by definition, all these ordered pairs of the form M, M are going to land in the relation R. There are other ordered pairs as well in this relation, such as 2, 4. Because by definition, an ordered pair A, B or M, N will belong to this relation R if M divides N. So, is 2 dividing the number 4? Obviously, 2 2s are 4. It means that 2 divides 4. So, by definition, 2, 4, the ordered pair 2, 4 is going to land in the relation R. So, besides the ordered pairs of the form M, M, in my relation R, there are other ordered pairs which are not of the form M, M. But I need, according to this definition, just one thing. I just have to check one thing for this relation R to be reflexive. That is, every natural number M must be related to itself. Okay? So, clearly, this relation, the relation of M divides N on the set of positive integers, is a reflexive relation. Until now, I have told you that when is a relation on a non-empty set A a reflexive relation? A natural question arises, when a relation on a non-empty set is not a reflexive relation. So here I have a question. When is a relation R on a non-empty set A not a reflexive relation? Now, if you are asking this question, it simply means that you are trying to negate this part of the definition. That is, if every element A of the set A is related to itself, only then we will say that the relation R is reflexive. Note down that I am using the universal quantifier every. So, in logic, if I want to negate this statement, here I have in my definition the universal quantifier. And according to the rules of logic, if you negate universal quantifier, you are going to negate it by the existential quantifier. That is, there exists or there is. It is saying me that every element of the set A must belong to itself. Only then that relation is reflexive. So what if every element of the set A is not related to itself? So to answer this question, I am going to negate this part of the definition. So after negating this part, I mean this, if every element of A is related to itself. So what will be the negation of this statement? Every element of A is related to itself. Simply its negation will be not every element of A is related to itself. Okay? If not every element of A is related to itself, what does it mean? What does it imply in other words? It implies in other words that there must be then at least one element in the set A which is not related to itself. So the negation of the statement becomes this. What? So after negating this sentence, I get its negation this. Not every element A is related to itself. In other words, there is at least one element in A which is not related to itself. So logically, a subset R of A cross A is not reflexive if there is at least one element in the set A which is not related to itself. Only then we will say that that relation is not reflexive. Once again, in simple words, a relation on a non-empty set A is not reflexive if you can give me a single element, at least one element in that set A, such that A is not related to A through the relation R. If this thing happens, then we will say that that relation is not reflexive. Here is an example. Consider the set A whose elements are 11, 12, and 13. And this is my relation, and it includes the ordered pairs 11, 11, 12, 12, 11, 13, 12, 13. So, is this relation R on this set A reflexive relation or not? Now, clearly this relation is not reflexive. Why? In order to answer this why question, I have to apply this negation of this very statement. This I have denoted by this simply to remind me this is the negation of this statement. So this relation R is not reflexive. Why? Because this rule, this negation of this statement tells me that R, a subset of A cross A, is not reflexive if you can find at least one element in the set A which is not related to itself. So let's apply this principle to this very example. 11, 11 is in the relation R. Okay, no problem. 12, 12 is also in the relation R. Now, this rule or this negation tells me that R is not reflexive if you can find at least one element in the set A which is not related to itself. Clearly, 13 is in the set A, and as you can see, 13, 13 does not belong to the relation R. So, according to this negation, this relation R on the set A is not reflexive. You should note one more thing here. If A is a non-empty set, we know phi is a subset of every set. Isn't it? Yes, it is. And as you can see, no element of the set A is related to itself through the relation phi. So simply this phi satisfies the negation. So phi is simply not a reflexive relation on a non-empty set A. If I replace the set A by the empty set itself, then there is a different story. And inshallah, I will discuss that story in the next video. Thanks a lot.